today, and welcome to today's class. Today we want to look at a concept in mathematics called the set theory. When we say set theory in mathematics, it is a notion that was defined by Georg Cantor in the 19th century, when mathematicians are looking for a concept where you can have an intuitive understanding, of what functions or mathematical functions are, or infinite set. So where Georg Cantor developed the set theory in the 19th century, there were famous mathematicians of that time who supported him, and today they leave us with the quotation that no one shall ever expel us from the paradise that Georg Cantor has created for us. Okay? So set theory today has now been using for different concepts in mathematics, most especially concepts that we can use to develop the functions and its continuity, infinite set, and so on and so forth. So when we say set, it is a collection of distinct objects. When we say distinct objects, these are objects that are well defined. Let me give an example of a well-defined set. If we say the set of even numbers, this is a well-defined set, because immediately we say set of even numbers, one can think of a number which has multiple of 2. Then I can say the object of this set will now be 2, 4. Okay, these are positive even numbers. Okay, from the negative side, we will think of -2, -4, and so on and so forth. Okay, in terms of maybe place or people, let's use for example place. Let's say the set of all cities in Kwara State. Okay, this is a defined set because you can begin to mention the cities that are in Kwara, such as Ilorin, Ofa, and so on and so forth. Okay? Also, we can talk of a set of all states in Nigeria, for example. Okay? This is a well-defined set because beyond that we have 36 states plus the FCT, and then we can talk about a set of all countries in Africa, or set of continents in the planet, on the planet Earth. Okay, this is a well-defined set too. Or we can say set of planets in the solar system. Okay, these are well-defined sets. Okay, we can even come to the maybe examples of what we use in our home. Set of all kitchen utensils. This is also a set. Okay, but what we will not call set, okay, that is items that are not well defined, is saying the set of all beautiful ladies on Kwasu campus. Beautiful ladies in quotes is not a well-defined set, okay? Because there is no such property for us to identify the ladies who are beautiful and the ladies who are not. Okay? Let's come back to mathematics. When we define sets, generally, we define sets as a collection of distinct collection of distinct objects. So as mentioned, okay, we can begin to reason what are these distinct objects. Okay, so when we say this objects here, we refer to a notion called elements. So objects are usually called elements. Okay, elements of a particular set. Okay, so those items we have mentioned earlier are what referred to as element of set. Okay, and so when we say a well-defined set has to be in a particular arrangement without minding the order. Okay, let me explain this. But before that, when we say set, we usually denote a set by curly brackets. These curly brackets are referred to as the band of the set. Okay, let me say, for example, if I want to say the set of all positive integers less than 5, the set of all positive integers less than 5. Okay, so I'll start the band of that set, okay, with curly brackets. Then I'll now list the set of positive integers. Okay, after the last number, I'll close it with this left brace. Okay, so this set will be the number 1, 2, 3, and 4. This is the set of all positive integers less than 5. Okay, so the items 1, 2, 3, 4 are referred to as the element of the set or the object of set. Okay, so here now, if you want to say that, if you want to know the membership of the set, okay, there is a symbol we use. This symbol is written as this. Okay, just to denote a membership of the set. Let's say, for example, if you are given this set of positive integers less than 5, the number 1 here is the member of the set. Okay, the number 2 is also a member of the set. The number 3 is also a member of the set. While the number 4 is also a member of the set. Okay, now if I want to write a non-membership of this, a non-member of this set, okay, one can write in this form. For example, the word set of all positive integers less than 5, you want to sound confusing, but if I say 5, is 5 member of the set? Though when I'm altering a statement of the in this set, okay, I say number less than 5, but intuitively the number 5 is not part because we mentioned less than but not equal to. Okay, so in this case, a non-member of this set will be number 5, so we'll cross it to show that this 5 is not a member of the set. Okay, so this is about the membership of set, and it is possible for us to have a set with no element. Okay, so in this case, we usually denote this type of set with the symbol left and right braces without anything in it. Okay, not even a dot. Okay, you will recall when we say object. Okay, if we put a dot there, that's a point. Okay, a point in between here will mean this set has an element. Okay, but we should not make that mistake. If you are representing a set with no element, we call it an empty set, and this is the symbol we use to note that, or we use the symbol phi. Okay, the symbol phi. We use either this or this to connote the set, an empty set. Okay. Also, when we say set in mathematics, we usually use capital letters, okay, to represent set. Okay. Let's say, for example, the uppercase such as A, B, C, okay, can be used to denote a set. Let's see, for example, again. From the first example we give, we can say let A denote the set of all positive integer or positive integer numbers, okay, less than 5. Okay, so here what we do is this: A is equal to 1, 2, 3, 4. Okay, so this statement alone that A should be the set of all positive integer less than 5 is this. Okay, and as such, from the membership we discussed earlier, okay, since you know that this set is A, okay, the element 1 is a member of A. Okay, and as we said earlier, the number 5 is not a member of A. Okay, so this is how we use some of these notations in the set theory. Okay, aside the uppercase A, B, C to Z, there are other special letters called the glyph letters that we use to represent some special numbers, some special set of numbers. This special set of numbers are conventional numbers that are recognized worldwide in mathematics. These are natural numbers. Okay, we'll say natural numbers. Okay, we use a letter, but in this case, not ordinary letter. Okay, but a letter with a glyph symbol N. Okay, we use this N to represent natural numbers. Okay, so if I want to define this set now, I will say a set of natural numbers, a set of all natural numbers is defined as N equal to 1, 2, 3, 4, dot, dot, dot. Okay? Another name for this set of numbers is the set of positive integers. Okay? In our in the usage, we call it the counting numbers. Okay? So we have other symbols, okay, that are special, that we use special letters for. Okay? The set of all integer numbers. Okay? The symbol is Z. Okay? And this contains the positive, the negative, 0 integers. Okay? So we also have another special one, that is Q, set of rational numbers. We have I, set of irrational numbers. We also have R, set of all real numbers. We also have C, which is set of all complex numbers. These are special types of letters, okay, we used to represent the 6 conventional numbers in mathematics. Okay, having said that, so let us also look at another concept under the set theory, which we refer to as equality of sets. When we say two sets are equal in mathematics. So let's quickly see this. has to be more than one set. So for easy understanding, we'll consider two sets. Okay? So we say two sets. I'm using A and B now. Are said to be equal if they each contain the same element. Okay, so in this case, if two sets ask the same element, not minding the order of that element, we say they are equal. Okay, so in this case, we'll use the notion of equality, okay, to say that A is equal to B. Okay, let's see, for example, if A is given as 1, 2, 3, and then say B is equal to 3, 2, 2, 1. Okay, if you look at this set, the setting contains the element 1, 2, 3, and B contains 3, 2, 2, 1. Okay, this is deliberate, and deliberately repeated 2 here. Under the set theory, when listing our element, if you know, or say a distinct object, 2 is distinct here. No matter how many times it's repeated, okay, in the output it should be 1. Okay, so 2, 2 is just one number. Okay, so I can write this set, okay, as since 2 appear once, I can write this as 3, 2, 1. Okay, and even if I do not, okay, you should know that 2 is just coming once since it is distinct there. So without minding the arrangement of the set, okay, we say that A is equal to B. Okay, so otherwise, if they do not have the same element, we say they are not equal, and we use the non-equal sign, which is this. Okay, two sets are said not to be equal if they do not have the same element. Okay, even if it's at least one element that is, for example, if we have A to be 1 and 2, there is no 3. Okay, I want to relate A and B. In this case, A is not equal to B because they do not have the same element. The first set here has 2 elements, while the second set has 3 elements. Okay, 3 elements that are distinct. 3, 2, 1, distinct. Okay, this one has 2 elements that are distinct, so they are not equal. Okay, so let us also look at the cardinality of a set. Okay, this is straightforward. When we say cardinality, it is the total element of a set. Okay, for example, if you are given, let's use this again. If this question comes up, that what is the cardinality of this set? The cardinality of the set A is noted by the absolute value symbol. Okay, the cardinality of A is equal to 3. This is because this A contains 3 elements. Okay, without minding this one, 1, 2, 3. Okay, that is the cardinality of B here is also 3 because it has 3 elements, 1, 2, 3. Okay, so that's what we mean by cardinality of a set. So if you have a set of 10 elements, the cardinality of 10 distinct elements, the cardinality of that set is 10 if they are distinct. Okay, but if there are some numbers that are repeated there, okay, we first of all write it in a distinct form, in such a way that each element will appear once before we determine the cardinality of that set. Okay? So when we say set can be represented in three forms. Number one, the listing form. Okay, let's say I'll be using an arbitrary set A here. Okay, so let's say A is the set of all positive integers less than 10. Okay, set of all positive integers less than 10. Okay, it means I can write this in the listing form. 1, 2, 3, 4, 5, 6, 7, 8, and 9. Okay, this is a set of number in a listing form. Okay, as you can see, we list the number that are positive and less than 10. Okay, the second one, so under the special numbers, we consider some examples of these two, and now they are related. Okay, so the other one is the word form or wording form. Okay, what's the word form? I can write, okay, the set A now. I can say A positive integers less than 10. Okay, this is the wording form. Okay, sometimes this is usually go with the last form that we are about to talk about. Okay, we call this the compact form. Okay, so usually mix of this compact form in the case when we have a dot which is semicolon. Okay, in English, but in this case, we refer to this as such that. Okay, there are of two types. Okay, so that we use this bar to represent such that, or this full column. Okay, this can be used in place of this. So, in terms of what we have here, okay, we want to write the positive integers less than 10. Okay, so we want to write this in a compact form. So this will be A equals to set n such that the set n in n which is a natural number, okay, such that n is less than 10, okay, such that n is less than 10. So this is a compact form. So if I want to write this in a listing form, this is how it will look like. Okay, look at this. N is a natural number and n, okay, is less than 10. Okay, it means we will begin to list this n when n is 1 here, when n is 2, when n is 3, when n is 4, up to we have this condition. Okay, so generally when we are using this compact form or the set builder, okay, there are three things involved in the curly bracket. The number one is the element of the set. First, okay, the conjunction of, the linking word, semicolon, that will tell us what the property will be. Okay, so such the element such that the property, okay, the property will now be, in this case, will be the property of the n. Okay, because n is what is in the element of the set. Okay, any property that will be here must link with the symbol or the letters we have used here. Okay, so this is how we represent different kind of sets. Okay, so now let us now represent the 6 conventional numbers in mathematics with this three forms, okay, or most especially this first and the third, okay. So let's see them one after the other. So I will continue the example, okay, but we show that they are different. We'll call this example 4. So what we want to do is to give examples of the 6 conventional number that we have, and then we want to represent them using any of this form. Okay, so the natural number, okay, we have said earlier in the definition that it's a set of number 1, 2, 3, 4, dot, dot, dot. Okay, this continue to infinity. Okay, so number 5. So this now is the listing form. Is a listing form. Okay, so we can have this. Okay, we can write this by this form 2 and 3. Okay, okay, we can say x such that x is an integer number. Okay, so it means we'll write all integers. Okay, ranges from in listing form now. Okay, so we have -3, -2, 0, 1, 2, 3. Okay, so this is in listing form. Okay, and we also have this one form. So number 6, we can write the rational number in a compact form. Okay, in fact, that is the only way to represent this, because the set of elements here can't be infinite. Okay, and there is no way we can, denote that other than this. So this is the set of elements A over n such that A is a number of the integer numbers. Okay, the numerator here is an integer number, and the denominator is a natural number. Okay, so you see this example going in line with this compact form. Okay, this any element we can get from this operation, okay, are the element of the set of rational number. Okay, so having said that, so let's look at another example. Now this time irrational number. Okay, when we say irrational number, this number cannot be written in the form this, and of course we can simply write this in the form x. Okay, it should be x such that x is not equal to a over n for a in z and n in n. Okay, all the set of numbers that we can get, okay, in which this x will not be equal to this. Okay, I think this x cannot be written as the ratio of two prime numbers. The ratio of 2 prime numbers. Okay, so let us also look at another example that we have. Example 8. This is the real number. Okay, we can write this as x. Okay, such that x is a member of the set Q. Okay, this symbol is known as a disjunction under the logic, and it's used to represent a set like something you know of 2 sets. Okay, so this R is a set x. Okay, such that x is a member of Q or I. Okay, we'll know before now that this Q is rational and this I is irrational. Okay, So this is how we can get this. Okay, and finally the complex number. Okay, this number is the set this. Okay, such that a comma b are real numbers, and then this I, okay, is imaginary. Okay, is imaginary number. Okay, so you'll see from here that these are really the compact form of a set. Okay, irrespective of the set, we can have different forms of different forms that we can represent them. Okay, there are other ones, okay, which I would like to give you as exercise. Okay, so in our next video we shall be looking at a subset of set. Okay, what I have just defined here is just an introduction of what a set is. Okay, now next time we're looking at a subset of a set. Okay, and some of its properties too. Okay, but before then, let me give you some exercise to work on before the next video. If you want your time, you can take time to look at all these exercises. Okay, so bye for now.